Please welcome David, who will talk about Chrome exploits.
Nice. I won't. I'm not talking about Chrome exploits, but that's okay. We got this, guys. It's an open source conference. Hi, everybody. No slides. That's fine. Yeah. All right, guys. Everybody focus up here. There are slides. I swear I made them. I thought about not doing it just because they might not come up. There we go. Cool. All right. So my name is Juan Andrés Herrero Saade. JAGS is fine for everybody. I direct research over at Sentinel Labs, Sentinel-1. And we're going to talk about a project that I called AlphaGolang, but in reality, just talk about sort of reverse engineering Golang and what hunting opportunities kind of come up based on that in particular. So the purpose of this talk in reality is just to try to get folks to be a little bit less daunted by Golang. And I want more of you to start sort of focusing on Go malware, you know, feel a little less intimidated by it, maybe learn to love it a little bit. The truth is that, like, a lot of reverse engineers have learned to hate Golang, and that's understandable sort of in the paradigm how things were working in the past few years, but I don't think that that's a reasonable expectation now. So I kind of want to update that. The truth is that you shouldn't hate Go. You should hate Rust instead. And you know, if we can all agree on that, then the real purpose of this talk is that if you pay attention to the state of the tools now, you'll realize that we're actually in a really good place, and we can get into an even better place when it comes to reversing Golang, but we could use a little bit of help. So I kind of want to like get folks up to speed and then do this general call for action where folks might be able to contribute a little bit more. So the structure of this talk real quick is we're going to very quickly go over some of the theory, like how some of the stuff works with Golang, compiled Golang, and then some of the pros and cons, and then why the malware ecosystem is developing the way that it is. And then in practice, you know, I want to talk about some of the things that we've been able to enable with what I call AlphaGolang or with IDAPro and sort of parts of Binja and so on, and what we could be doing better, right? So to understand Go binaries real quick, well, how many people here have had to reverse Go binaries at some point? Show of hands. All right, that's a pretty good number. Did all of you hate it? Was it terrible? Yep, all right, got it, cool. Not as bad as Rust, I promise. So real quick, my friend Ivan talks about Go as just fascist Python, right? Like at some point, somebody looked at all the mistakes that people make on Python and go, this is unacceptable. It's not, like, there's ways that we can fix this if everybody would just commit to doing them the right way. So in reality, when you're writing Go, you just have to think of it. It's statically typed, it's statically linked, it's automatically formatted. So for anybody who has worked at Google in the past, like this is like a readability manager's dream, essentially. Like you're forcing everyone's code to look the same. It's very strictly enforced in the sense that like comments, even comments for like exported functions are supposed to look a certain way. You can't have unreferenced imports. You can't have unused variables. You have to do manual error checking, etc. And the idea seems to be to do a lot with a little, which is very interesting because it means that a lot of folks are relying very heavily on the like standard libraries, which can be very good for us, right? So the benefits for programmers is that it's very fast, concurrency is super easy, and in theory, it's, you know, multi-platform, cross-compilable, and it has painless portability. We're going to see how that kind of breaks down for some of the malware folks, but that's sort of the pitch. The benefits for malware developers are all of that stuff, plus you can hide your user-generated code in a sort of bulk of standard library code. So you're looking at a 17 megabyte binary that has like 50 user-generated functions. What's wrong? Okay, got it. There we go. Is that better? There, better. Cool. Yeah, okay, got it. I can stop breathing on you guys, great. Then you have like tons of open source tooling to choose from, particularly like the malware ecosystem, like the red teaming ecosystem has been developing very healthily on Go. And you can annoy a lot of reverse engineers without doing absolutely anything. Like, we're not even going to talk about obfuscation at all. So what are the problems? The binaries are massive, which is easily fixed by UPX. You can take a 15 megabyte binary and make it a 1.5 megabyte binary with like one command, which is why you'll see so much Go code UPX packed. It is very verbose, but you can strip the symbols to some extent. You can also do obfuscation, which frankly, I mean, I hate the obfuscators that are available for Go, but we can still work with this. And Go programming is a sort of new paradigm that you kind of have to get used to, but you can also half-ass your transition into Go by just using C Go and OS-specific implementations, which is why I say that the portability is painless, but in reality, like for example, a lot of ransomware developers will start writing in Go and then use Windows-specific implementations, and the portability is broken. So you can't really take that ransomware and just cross-compile it for Mac. So the Go malware ecosystem has been increasingly growing. It's gaining a ton of traction. Obviously, you have your typical IoT garbage, a lot more ransomware, and then nation-state operations that are starting to rely on Go in an increasing manner. It's either something about the cross-compatibility, at least on the IoT side, the performance on the ransomware side, like if you can encrypt things very, very quickly, and then analyst inconvenience, I think, on the nation-state side to some extent. So real quick, if you're looking for things to look at, plenty of crimeware with colorful names, not quite as good as David's presentation, but some names there. And then plenty of APTs, particularly a lot of Russian APTs if you look at this list, including the last two were pieces, well, let's see. The middle three, Goldmax, Goldfinger, Tomaris, these are all things related to Nobelium, which was, you know, SolarWinds and all that wonderful stuff. And then Party Ticket and Desert Blade were some of the components that we've been dealing with on the Russian invasion of Ukraine. So Desert Blade in particular is a really recent wiper they've been using. So there's that, but there's so much more. I mean, obviously, the more daunting a piece of code looks, the less people want to analyze it, the less people want to hunt on it, the less you notice that there's more stuff under the surface. And if you look at just basic similarity analysis like SSDeep, or TLSH for similarity, because there's so much library code, it's very easy for two totally different pieces of code to kind of pass the threshold as very similar samples. So it definitely needs a little bit more attention. So okay, let's get to the more interesting stuff. How do we analyze Go binaries? So we're not doing a hello world cop-out. We're going to talk about, like, all the images and examples are going to be real malware. And of course, we're going to be using IDAPro. You know, of course, you know, Peter, forgive me. You know, Binary Ninja is so much better, but, you know, old habits die hard. We're definitely not doing Ghidra. Those are government handouts. And there's some forks in the road, right? I know that not everybody can afford the latest and greatest IDA because it's insanely overpriced. But unless you're using like the Yucha IDA that North Korea keeps handing us. But there's some differences there that are worth mentioning, right? Before 7.5, compatibility in IDA is really bad. So we added a couple of scripts that might help folks who don't have access to the newer stuff. After 7.6, we get the folder view API, which is, if you're not using folder view, it is actually really nice. So right click, enable that in your functions. And then 7.7, somebody gets a brilliant idea to copy a piece of what we developed in AlphaGolang, and they kind of fuck everything up. So we're going to deal with all those things as we go along. So 7.5 or below. What's the real issue? When somebody strips a Go binary, what gets removed is a segment called Go PCLN tab. It's a really important part of how a Go binary is built and contains a lot of the information that you want. In reality, Go PCLN tab is just, it's perfectly sort of pointed out in a structure. And when you strip a Go binary, you're not actually removing any of that information. There isn't an entropic process involved. There's just less of a clear indication of where things are pointed to. But it's important for reverse engineers to understand, just because you stripped it doesn't mean the data is gone. It's just not as easily correlated, but you can still brute force your way through this. So if you look at this, right, like the Severity sample, IDA loads up the segments, there's no GoPCLN tab, right? So we can definitely rebuild it ourselves. So you take a strip binary and you just look for the segment start based on these heuristics, right? It's going to start with this. The segment end, you can brute forces, right? At what point do we just get a bunch of zeros as padding between these things? Basically about 2 to 3 quad worth of zeros. And then the result is that we can essentially say, this is where GoPCLN tab should have been. We recreate the segment. And what you get is this super nice piece of information about where every single function in the binary should be. So you don't have that problem that you would have with normal code where it's like there are functions, but they're not called, so maybe you have them sort of unreferenced or you have to manually discover them. You can actually get every single function that's in the binary. A few little tidbits there. GoPCLN tab wasn't always there. It wasn't always documented. It isn't necessarily used in the same way. There's variations, etc. But for the most part, like, you just have to understand that one tidbit. Then the problem is, well, what the hell are all these functions, right? We're talking about 4,200 functions. Most of them have no names. Who the hell wants to deal with that? Pretty daunting, pretty terrible. So how do we discover and rename all functions? Not most, but all of them. Well, we can just walk PCLN tab and check the .text offsets. It'll actually discover a few more functions for us. Right now we're up to 5,000. And then when you do that bit of correlation, you actually get all of the names back. And I mean all of the names back for all these functions. So we can just take that same pane, and what you're going to look at is this, right? Package sync, atomic, etc., runtime stuff, so on. So great. But what the hell do we do with all that? It's still 5,000 functions. So let's get a little bit organized, and more importantly, let's bubble up user-generated code, because that's really all we care about. With a language that is so reliant on standard libraries, why would it's like reversing OpenSSL, right? Like, if you fell into that trap, the rest of your day is wasted. We don't want to do that here at all. So this is where Golang fascism and IDA 7.6 plus features come to bear, right? Again, if you're not using folder view, you're really missing out. So most Go code relies on these standard packages like the fumpt library and sync and buff.io, and it's all really well documented, but more importantly, it's all really standard. And there's really no reason for it. Then the rest of the code that you're likely to run into most likely comes straight from GitHub and is labeled as specific GitHub projects. So again, you look at something like this, it's Golang crypto. Why on earth would we ever bother reversing any of that stuff? It's like, it's in the tin. You could just read that. So we don't want to waste our time with any of it. So, like I said, 7.5 introduces folder view. 7.6, more importantly, introduces the folder view API, which is where we're going to get our gains, right? And we're going to focus only on this user-generated code. So if you look at Goldmax or Sun Shuttle, again, part of the SolarWinds Nobelium sort of cluster of stuff, you have all of these functions. They're nicely labeled for us. But if we run this neat little script, you can actually just sort these all into folders and then automatically sort all of those into folders with priorities in them. And what you really end up with is, hey, these are the only functions you should probably bother with at all. At the end of the day, if I remember correctly, that is 20 functions to analyze out of however many thousands, right? Much nicer time. And I guess Hexrays liked our idea because then IDA 7.7 tried to do a similar thing and instead broke our script and didn't properly categorize any of that stuff. So the script has been refactored. You can still sort of use it with 7.7. So it's working. You can prioritize your stuff. So maybe that's like, as a reverser, you're like, okay, we're ready to go. This is great. And in a sense it is, but the truth is that there's still kind of a lot more there that we could be taking advantage of, and that doesn't work quite so natively. So when you look at a function in Go, this is a fairly familiar thing. Like, you look, it's like it's loading a string, And what you get is these giant blobs that are obviously not the way those strings are supposed to be formatted. And it just keeps going, and it just gets worse and worse. And the reason for this is fairly simple. Go doesn't terminate, they don't null terminate strings at all. It actually loads them in a more safe way by specifying what the length should be wherever the string is called. And the compiler actually takes the liberty of arranging strings in an incremental length way. So you get, you know, length 4, 4, 4, length 5, 5, 5, 6, 6, 6, 7, 7, 7, etc., which IDA has no idea what to do with, and it just looks like this ginormous blob. So that sucks. It's unnecessarily inconvenient. Sometimes it is actually genuinely confusing, like if you're looking at URI paths and stuff, like where does one thing end, where does the other one begin? So we can definitely fix this just by focusing on the, casting the strings by their kind of load heuristics. And this is where I'm honest, I sort of borrowed and hopefully improved Tim Strasser's Golang loader assist from a few years back. I just kind of had to refactor it a bit to work with the newer IDA APIs, because of course you should change the IDA SDK and APIs every 6 months, just in case. So that got fixed, and what you do is you just focus on these string loads, right? Like if you look at this, we have a reference to load a string at a certain location. It's a giant blob, but you see the length is just being loaded right there, and we can easily sort of just recast that into what it should be. So you look at something like this, is a little closer, and we don't really need to take the time to do that manually. So instead, what we would do is just load up the script, let it run for a bit. It can be a bit much since these binaries are so big. You remove these giant string casts, you let them sort of be recasted in a more intuitive sense with those heuristics, and eventually IDA finishes running that script. And you get a much nicer set of strings, and then if you just kind of refresh your decompilation, everything makes sense, right? So it's not perfect. It can use some help. I'm going to talk about it a little bit more towards the end, where like this is one of those things where I could really use community help to kind of refactor how that's done, because Tim's idea was the right one, but the implementation isn't perfect. So like we could use some more understanding of the right load heuristics. We could probably use a better way to traverse the binary, and maybe take advantage of the fact that like the compiler is loading them by length. So like we could definitely fix this better, but I haven't exactly had the time to do it better. So how about object type information, right? Again, another bit of entropy that can really dog us. This is where Ivan, or Justice Rage, comes to the rescue. He submitted one of the first sort of community contributed plugins, and it turns out that you really can just walk a different table and get all of your object types back, which in Go is particularly important because all the runtime make channel, make object functions, for example, they can be quite confusing unless you get sort of that exact information. So we get the correct seed types, it renames them for you, it even handles some of the arguments, and of course adds human readable names. So that's already in there, it's already quite useful. So let's talk about sort of the unique benefits for hunting malware written in Go. And I hope that some of you have already kind of like been catching on to what I'm talking about, but essentially I can't think of any other modern language where you can recover not just so much information about the original source code, but have it automatically bubble the only things that you need to look at all. I wish C worked this way, I wish C++ worked this way. But essentially, I can, before I even start analyzing a binary, I can have an exact idea of the functions that the developers wrote. I can have an exact idea of only the strings that are referenced by those user-generated functions. It's actually quite beautiful in the sense that you can subsequently take that information and also automate your hunting, right? Like why not generate YARA rules that are based specifically on that code, generate YARA rules that are specifically referencing those strings, And even more importantly, just bubble up only those functions for analysts to look at and not waste any time whatsoever reverse engineering things that you shouldn't. So the state of things right now is there's a lot of areas that we can improve and a lot of opportunity, and this is kind of where this turns into a bit of a call for action, right? You can look for AlphaGolang on GitHub, you'll find it right away, and you'll realize that I suck at coding and there's a lot of things that we could improve, but some of the things that I really want to bubble up. We talked about obfuscation. In reality, obfuscators can't really change the structure of Golang binaries because if they do, they'll break them, which is why stripping doesn't really work. If you were to go in there and really mess with some of these symbol tables and so on, those binaries will just stop executing. That's not to say that someone in this room couldn't get really clever. I hope you don't, but you could build some packers and so on. But the truth is that that information is there. So this is where Luna should be saving us, right? If I just turn all of the names into like garbled text, but we have a signature in the cloud for what that function should have been, in theory, we should be able to pull the authoritative names what those functions are. The problem is that Lumina server is entirely uncurated. So all of the confused people who've been pushing those garbled names into the Lumina cloud are in effect screwing the rest of us over because now IDA auto-muddles your IDB when it shouldn't. So make sure that when you go in there that you actually revert the Lumina changes and only really use it when you're in a state where it's like, this is obfuscated and we should hopefully be able to get stuff back. But this is where I'm like starting to ask for them to give us an API for Lumina so that we can auto-revert the changes because they're auto-applied. And then hopefully we can find some ways to better handle that. The string recasting script, as I said, it needs refactoring. It needs more of the modern heuristics. It works in most cases, but when you get a 25 megabyte Golang binary full of these blobs, you're going to have a bad time. You know, we can always handle function types and object structures better. Ivan provided the script, but it's not tested for all of the edge cases of cross-compilation, so sometimes you don't have the right segment name. We should probably figure out the heuristics for some of that. We could definitely improve handling of arguments. Why? Because if you look at Go, you can pass a function multiple arguments and you can return multiple arguments. So the way that it handles that is the caller stack is actually allocated to be much bigger, handle all these arguments, and then there's a call to a struct. Sorry, it passes a struct that includes the return arguments, and obviously Hexrays doesn't know what to do with any of that. So there's a lot of opportunity there for us to kind of fix this. And then I mentioned sort of this hunting gains, and I've been sort of playing with some of it. I'm going to push the scripts up in the next couple of weeks, but the idea is for those of us that are doing hunting, you could almost get away with not looking at the binaries if we can get this workflow perfect. Because if all I care about is what else relates to this code, then all I need are YARA rules that hunt for the opcodes in those user-generated functions with some wildcarding, and YARA rules that hunt for the strings specifically referenced by those user-generated functions. And the rest of it is, you know, how much do you care to understand what's happening here? From the hunting perspective, your job is done. Like from that point forward, you can easily pivot to any other Go code that functions in that way. So on that, I really want to thank obviously Tim Stresser, whose plugin I essentially cribbed and tried to fix. Milan Bohacek from Avast, who actually helped me get the folder view API working because Hexrays doesn't really do documentation for human beings. Joachim Kennedy from Intezer, who's done a lot of work on Go binaries even before I put up this plugin, and he does it in R2, which means he's some kind of masochist, but at least we can work in IDA. Mike, who was the first person to get me to write Golang and learn to love it, and then Ivan, who not only provided the struct types script, but has also made a pretty nice Go reversing training that you guys might want to check out at some point. Shameless plug, since the conference is not being run by anyone other than the community volunteers right now. LabsCon CFP is open. Do please submit some great talks. Join us in September, labscon.io. We're really trying to get some more of the threat intel side of things, and would love having some of the REs involved. And maybe you can show us what you end up making out of AlphaGolang. And thank you guys. If there's any questions, if there's, if people want to rush out to lunch, I will not be offended in any way whatsoever. And thank you so much for sticking around way over time. And yeah, learn to hate Rust reversing, but Golang is actually in a much better place than even a lot of the languages that we're fairly comfortable with. So thanks, everybody. Anybody? Anyone? Oh, we have one in the back. You can probably just yell, man. Yeah. I mean.
Do you have any ideas for how to handle the multiple return value functions?
It is a mess. It's an absolute mess. Let's see. So we've been talking about this a little bit, how to handle it. I mean, obviously the arguments coming in, not so problematic. The arguments going out. We've been talking about sort of trying to rebuild those structs on the fly and pointing them out, but I'll admit that I don't get along or understand very well the hex-race decompiler API, and that's where we have to do the real work, right? Like that's where we could almost force it to have those references in there in a way, but I do think that hex-race is going to have to come up with some way to reference this, because the way the pseudocode allows right now, it just has no option for this. So the best that we can hope for is just referencing a struct or referencing something in the stack that says these are the pointers to your values. But yeah, we haven't had much more luck beyond that. So if you have some good ideas, please jump in, guys. Like the GitHub, I've been working this one alone, then Ivan came along. I'm really grateful. So any contributions we'll be thrilled for. Anyone else of the not hungry people? All right. Thanks, everyone. Thank you so much. I appreciate it.